pastores y ahora nos va a dar esta plática de investigación en celdas solares. Entonces, adelante, Chandra. Muchas gracias por aceptar la invitación. Chandra, Chandra, ¿puedes empezar?
Ya, perfecto. Ya, buenos días a todos. En todo país de latinoamericano, pero muchos de mis amigos y amigas están escuchando de la India también. Para ellos, buena noche, porque en la India ahora el 7 de la noche, ¿ya? Y además, muchas gracias al profesor el Arturo, el profesor mexicano, conocemos el desde 2018, para su invitación, para la charla. Voy a explicar el muy básico, la avanzada investigaciones por las fotovoltaicas, como yo trabajo en Antofagasta y la India y acá estoy trabajando también. ¿Ya? Eh, Ahora trabajo en la Universidad de Santiago de Chile, en capital de Chile. Ahí tiene la universidad, el dentro. El edificio, él llama así CEDENNA, el edificio de investigaciones. Tiene todo lado, como el primer piso, segundo piso, tercer, el cuatro de las cinco pisos, nosotros trabajamos. El grupo, el profesor Juan Spring, el decano de el ciencia de facultad de ciencia y además el director de investigación también. El amigos y las amigas. Ya. Ya, primero voy a hablar o discutir por las fotovoltaicas o celdas solares, pero quiero discutir o hablar en inglés porque para nosotros está fácil para aprender la cosa, pero el indio está acá, no puede aprender porque para la inglés está fácil para ellos, pero ustedes pueden preguntar, discutir o su duda, pueden más explicar en español también, ¿ya? Ya vamos a explicar en inglés, ¿ya? Okay. So today I will discuss about fundamental and advanced study of solar cell. So first question, why solar cell or photovoltaic cell or other alternative source? Why not fossil fuel? That is the fundamental question. I will start. I will begin from here. Okay. So I will explain one by one what is the aspect, what is the role, why we studied in that direction, and why we are focusing. So there is a few evidence towards the fossil fuel. This is data has released by DOE about the emission of carbon dioxide. And we had data from different zone, different region, and also when we see here, this data also released by government of United States of America in 2018. Around 37 billion ton CO2 has emitted. This is dramatical. And also when you see different, like in India, 2.6 billion, in European subcontinent, 3.5 billion, in United States of America, 5.4, in China is around 10, other countries, including Russia and the rest of the part is around 15%. And when we compare total, it's around 37% carbon emission that has recorded in 2013. Also, in 2021, United States released the data for energy consumption, like natural gas source, they use around 23%, coal, they use 23%, nuclear power, 8%, renewable energy, that includes solar cell, and wind energy, that is only 6%. And petroleum, that is quite higher than these, around 40%. These are the uses in United States of America, where they use petroleum around 37 to 40% in different industrial areas, and natural gases that they are using in transportation industry and rest of the place, coal And also renewable energy, that is 8%, including solar cell and wind energy and other source, only 8%. This data has released in 2022. And nuclear is 9%, that is distributed among all. So what is the alternative source of this fossil fuel? How we can stop the emission of carbon or CO2 or other such pollutions? So that could be one possibility to study about solar cell. I'm not sure about it is 100% true, but this is one source because we can go to wind energy or another green energy, but one source is solar cell. These are the data about crystalline solar cell, thin film solar cell, and other. I will discuss one by one. These are the first generation, where we have studied monocrystalline silicon based solar cell. I will discuss later the achievement of Martin Green and rest of other groups. In second generation solar cell, we try to study about amorphous silicon, gallium arsenide, and rest of the part like CDT, TDS based solar cell. But that problem is that efficiency limited. Amorphous silicon solar cell having 13 to 14%. This is maximum limit. And CDT or gallium arsenide is maximum limit. I'm not talking because they have given here is a theoretical data, but experimental, it's quite low. When we are talking about third generation solar cell, where we can get multi junction like heterojunction, 3-layer junction, 4-layer junction. Also, polymer based solar cell, dye synthesized solar cell, perovskite solar cell, organic solar cell, that comes under the category of 3rd generation solar cell. And these days, entire world is focusing or working towards the 3rd generation solar cell. And among 3rd generation solar cell, one another achievement is when we make hybrid layer of silicon with perovskite, that is called tandem solar cell. That is more effective than these all solar cell because experimental efficiency and potential and short circuit current is quite higher than these 3rd generation materials or solar cell. The story which began for solar cell in 1946 during the Second World War, and first solar cell was fabricated using selenium, which has atomic number 34 in periodic table and having very less efficiency is around 1.01 or approximately 1%. That is patented by United States of America. And you can search also this patent has recorded for first solar cell. If we are talking about silicon-based solar cell, then first silicon solar cell had been fabricated in 1955, and they improved the efficiency from 1% to 2%. But 2% is quite low, so we cannot utilize anywhere. But dramatical change that comes in solar cell, or especially I'm talking about silicon solar cell, because these days market or commercial purpose, silicon is dominating around 95%. Martin Green is the professor who is working in University of South Wales in Australia. In 2008 and 2009, he used silicon, texture silicon, with pyramidal shape, like something different. I will discuss later in my slide what he did. They didn't use the flat silicon. Instead of flat silicon, they used pyramidal shape or texture shape. And they achieved the efficiency around 24.9 or 25%. And open circuit voltage is, short circuit current is quite high. And fill factor de Janado, is around more than 80%. And later, everyone make a concept, we can go through silicon and we can enhance the efficiency, later merge the different metal oxide or different layer to understand how we can enhance the efficiency. These are the major results. If we are talking about 2020, during the pandemic, Corona, COVID-19, 4 junction solar cell that has recorded efficiency, theoretical efficiency, around 47 to 48%. See here. But this is theoretical, and this is for multi-layer junction-based solar cell. That is quite different to fabricate. First thing. Second, this is more expensive, so it is not easy to fabricate or design inside the laboratory. So we will discuss about the principle of solar cell, how it works, and how we can design inside the laboratory. So we will begin with fundamental p-n junction diode. It is more fundamental. P-n junction diode means when p-type material semiconductor and n-type semiconductor is sandwiching each other, then form a junction called p-n junction. This line is called depletion line, and when electron and hole near this line may interacted each other and diffuse or recombined. When this electron and this hole recombined, this electron, this hole recombined, created one current called as diffusion current. After certain time, there will not be any charge will present here in this region. This region is totally vacant. This region is called depletion region. Depletion means deplete. Deplete means to eliminate or remove carrier. So there is no carrier here. There is no charge here. That's called depletion layer. Once there is no electron hole here, then this hole and this electron has or have to reach this junction, but they don't have sufficient energy to cross this barrier. So we will use different biasing. I will discuss very brief here. We will use if we connect p-type silicon with positive terminal of battery and n-type silicon with negative terminal of battery. This is called forward bias. And once we supply from the voltage here, hole will move from here to here, electron will move from here to here, a certain voltage, a particular voltage, this depletion layer will vanish. And electron and hole will interact each other at a certain voltage. In case of silicon, that voltage is called 0.7 voltage. See here. From here to here, there is no current or leak, very minor current will increase, but a certain voltage, this voltage, once we increase voltage 0.1 volt, 0.2, 0.3, 0.4, a certain voltage like 0.7 voltage, this barrier will vanish. Once this voltage will vanish, it means the electron and hole which interacted, that would be independent of this voltage. Once voltage are getting increased at certain voltage, this current will be independent of voltage. I will discuss this graph later when I will discuss about the IV curve of solar cell. This is more important. This voltage is called threshold voltage in case of forward bias. However, in case of reverse bias, p-type, that would be connected with negative terminal, and n-type, that would be connected with positive terminal of battery. Okay. So see, here, when we supply the voltage, depletion layer become narrow. But in case of reverse bias, when we supply the voltage, depletion layer become wider. Once we supply the voltage, this is p-type, like positive ions that will interact by this side, and electron that will interact by this side. At certain time, this depletion layer become more wider. So one question usually asked, n-type, when we form n-type and p-type junction, then forward or reverse bias, which is convenient for super device like optoelectronic device, including solar cell, sensor, photodetector. So I will discuss later whether forward bias or reverse bias, which could be the better option to design the solar cell or other similar devices. So in case of reverse bias, the graph looks like this. I will discuss later. This current is called leakage current or saturation current. And in same way, there is a voltage, a certain voltage, in like here in forward bias. This part I will discuss later. Okay, so next I will discuss about the area. The questions come always in mind when we establish solar panel or solar cell, then which light they might absorb. So if we are talking about silicon, so you know much better, the band gap of silicon is around 1.12 electron volt. If we convert in term of wavelength, then that would be around 1000 to 1100 nanometer. What does it mean? It means a silicon-based solar cell might absorb light if they have wavelength in range of 1000 to 1100. In same way, if we are talking about gallium phosphate or gallium arsenide, in gallium phosphate, if you will see, the band gap is around 2.8 or 2.9. That means they will absorb the light which comes under 280 to 300 or 350 nanometer. That comes in range of ultraviolet to visible range. That is totally also depend on the band gap that I will explain later, because if light which is coming from sun or any source, that is whether absorbed by material or not, that is depend on band gap. If upcoming light have band gap approximately equal to the band gap, like in case of silicon, if the light which is coming, that would be equal to 1.12 electron volt, then that light could be absorbed by the material. These are the spectra where solar light might be absorbed. See, you can see this is visible range that is starting from 300 nanometer to 750 nanometer, and near infrared, like I'm talking about 750 to 900 or 1000. So solar is usually absorbed by different material in visible range and near infrared region. If we are increasing more wavelength, then there is no conversion of light. Okay, so this is the more fundamental and basic diagram of solar cell that you have probably seen everywhere. This is same way that I explain later. P-type layer, N-type layer. This is depletion layer. That earlier I said, if we take P-type material, N-type material, there is a depletion layer in between them. Okay. Here we use one glass lens. I will discuss the role of this. Here metallic tip, metallic layer, that I will discuss later. Here is one substrate base. I will discuss the role of this. Here we have provided the load to which electron can easily jump or flow. First question here come. When we design the device upper layer, that could be either N-type or P-type. If we are taking this is like this is N-type and this is P-type, so always we have to take upper layer is thinner, like narrow, and lower level should be thicker. I will tell you why. And also the role of depletion layer is more important here, because I discussed earlier in forward bias, depletion layer is more narrow, but in case of reverse bias, depletion layer is more wider. So first question, why we take upper layer is more thinner or more smaller? Because reason is when sunlight is coming from any random source, they must have to reach near the depletion layer or inside the depletion layer, because the creation of or generation of electron hole that may be carried in yellow range, this range. This yellow part is a depletion part, a depletion layer. So where depletion layer is more wider or more higher, then more probability is more electron and hole might be generated. So you see in forward bias, depletion layer is more closer. So if you use forward bias, then in case if sunlight is coming, then you will get less generation of electron and hole. But instead of forward bias, if you use reverse bias, then you have wider depletion layer. If sunlight is coming, then more electron and more hole might be created here in this type. If we use wider layer, then more electron hole could be generated. Next, if more electron and more hole will be created, that means electron have negative charge and hole they have positive charge. In this region, they might be neutralize each other, or in another word, they can recombine each other and enhance the rate of recombination. I will discuss later how we can eliminate it, how we can remove the rate of recombination. But rate of recombination is generally the electron hole which might be recombined in this depletion layer because of opposite charge. So we use metal strip here to attract some charge to eliminate or avoid the rate of recombination. So this metal strip has advantage to attract few charge that might reduce the rate of recombination. This glass lens we have used to protect our device or our solar cell. Same is here also. When sunlight is coming, sunlight energy should be equal to or approximately equal to this energy band gap. Then only that energy might be absorbed by our solar device. That could be the silicon based or perovskite or organic or rest of the thin film based solar cell. So keep in mind when we are selecting material, be precise, be concise. We have to check optimum band gap. So see here, these are the animation. When electron energy which is coming from random source in this region, and in generally in depletion layer there is no electron and hole, but there is an atom present in depletion layer. When sunlight is coming and knock to that particular atom, an atom will break, and electron and hole might be released from that particular atom, and electron obviously will move towards N and hole will move towards P. But here, if we supply huge charge or huge radiation, then like if we are supplying 1000 watt per centimeter square radiation, then by example 1000 atom may be broken. Then in case lot of electron hole might be destroyed or might be recombined. So we have to avoid. Here I will discuss this also. Okay. These are the most important characteristic called IV characteristic. This is nothing just equal to this one. This part you see, this is similar graph. Just I converted this graph from the origin software for our convenient. But this is don't be confused. This part is just like this graph. If real picture we will see, this graph will comes in this way. Okay. So these are the parameters that I will discuss. These are the solar parameters that I have to discuss here. One is open circuit voltage. I will discuss what is role of open circuit voltage, short circuit current, fill factor, solar efficiency, series resistance, parallel resistance, ideality factor, and leakage current, and some also parameter that I didn't include here, like potential barrier. I will discuss the role. D. Short circuit current and open circuit voltage. These two parameters comes here. What is short circuit current? That is more important question always asked by different place when we use solar cell or we use device. See, this is solar cell. When we connect this and there is a no load or voltage here. Okay. In another word, short circuit current is the maximum current when voltage is zero or there is a no voltage. So in your device, in your solar cell, you will get the maximum current that is called short circuit current. And you will get that current when voltage is zero. Okay. Second parameter is open circuit voltage. In opposite way, open circuit voltage is the maximum voltage when there is no current in circuit. See, in this case, when we disconnect our circuit, there is a maximum voltage. What does it mean? It means there is no current. So short circuit current means maximum current at zero voltage, and open circuit voltage is maximum voltage at zero current or maximum voltage where we will not get any current. This point here, see, this point, if we plot more precisely this point here and this point here, okay? So this point is called I maximum that you can get here and V maximum you can get here. So this point is called where you can get maximum potential. Here is short circuit current is maximum here, but current is maximum, general current is maximum here when we didn't make any short circuit. That is here. I will discuss later in this point. Okay. These are the parameters we can go further. first eta that represent solar efficiency. That is efficiency like output divided by input. Output means maximum current into maximum voltage divided by area into radiation. So maximum current and maximum voltage means here if you put your cursor, you will get maximum current. That current is here, and maximum voltage that you can get here. Area, how you calculate? If you use any wafer, like if you take this one, just you calculate through scale this and this. This is given like here, 2 by 2, 1 by 1, 1.5 by 1. If you are taking silicon, you can also calculate or FTO bit or ETO, any substrate that you can calculate the area that you have to put here. And radiation, different radiation you can use, generally 1000 watt per meter square or equivalent. That is also a factor I will discuss later. Radiation that is coming also affect our performance of solar device. This is fill factor. That is another important parameter that gives the squareness. Like your curve is more square, it means it has given more better outcome. I will discuss later. And RS is series resistance, and RSH is shunt or parallel resistance. Series resistance, I will tell later, is the combination of all resistance, like resistance of your material. If we are making contact here, then resistance of that contact. So total rejected contact that comes under category of series resistance. On another hand, shunt resistance or parallel resistance, that means when we make solar cell, then in P type there is a hole, in N type there is electron. But at same time, there is a minority charge carrier also present. Like in P type, there is a few minority electron, and N type, there is a few minority, that is hole. So once minority charge carrier will meet each other, they created or generated leakage current or saturated current. I will discuss later what is role of this current. So basically, this can be used to handle or minimize the leakage current or saturated current. Fill factor. How we can calculate fill factor? So here you can instead of in research paper and book, you will get J maximum instead of I maximum, or here you will get current density instead of current. In many places you see, the reason is we need to, if we have multiple data, we need to normalize it. So just we have to divide current with area, that area we have chosen. Instead of current, we write current density, that is more appropriate. So from this point, you can calculate maximum current and maximum voltage, that is IP and VP. Short circuit current you can get from here, open circuit voltage you can get from here. So easily you can calculate the fill factor. Fill factor that tells about the squareness. If we are talking about these two figures, then this figure has more square. See, it means in figure number 2 has better response, better outcome. In figure 1, see, here is a less square. It means here a fill factor is less. We could explain through different way, like enhance the series resistance, enhance the particle size. I will discuss later one by one. How we can calculate series resistance and shunt resistance? So series resistance, we can calculate, we can take slope from here to here. This part is basically gives parallel resistance when voltage is 0. Like short circuit current, where there is no voltage, you can get shunt resistance. And this part you can calculate series resistance when current is 0, because where open circuit voltage we can calculate, there is no current. So this parameter is more important. Okay. So now I will discuss the result which we have studied since 2018 at Universidad Católica del Norte, UCN, Antofagasta. So generally we have used three different material. One is silicon, that is silicon N type, silicon P type, silicon 100, 111, different on the conditions. Second is we have used silicon solar cell like this, that we have here also. And third is glass substrate, glass with coating of FTO and coating of ETO for different purpose. So here, the advice of my supervisor, Professor Antonio Sarate, was used to ultra thin layer, like 1, 2, 3 nanometer, 5 nanometer. The advantage to use that layer, because if we use upper layer is too thinner, then light can easily trap or penetrate or reach to depletion layer. So, and also see the advantage of this layer is more transparent. This is optical band gap. That is more important, as I discussed earlier, that you can calculate through optical absorption spectra, not directly absorption spectra. This spectra could be converted in absorption coefficient. Then you calculate the band gap. Okay. So I will not discuss here about detail of optical property because our focus towards the electrical or photovoltaic property. So these are the outcome. First result which we have reported, and this paper also published, you can see here in 2021, the enhanced light trapping nature of NiOx thin film deposited by magnetron sputtering on silicon solar cell. So we use two different conditions when be deposited through magnetron sputtering. So one is when supporting holder which is moving in sputtering, I keep in moving mode, and second I keep it fixed. So I have seen the different variation, like when we keep it fixed, that means we have gotten different outcome. When it was moving, it was different outcome. When sputtering holder was moving, then we have gotten homogeneous or uniform film. But when we keep it fixed, we have gotten lot of defect or lot of disorderness or non-homogeneous structure, but that was better for our purpose. Here we have calculated the series and shunt resistance through slope that I earlier discussed. And always keep in mind the value of series resistance should be less than 1. If you are designing the better device, then you have to keep always total series resistance or sum of series resistance should be less than 1. And also the parallel or shunt resistance should be higher. If shunt resistance or parallel resistance should be higher, it means it minimizes the rate of leakage current or minority current. And this resistance should be lower. It means if shunt resistance means resistance of material and resistance of contact, if that is less, then sunlight can easily reach the depletion region or depletion layer. This is similar graph that I have taken in logarithmic form to calculate ideality factor and leakage current. So this is well-known formula, you know, and here is eta that indicate ideality factor, and I naught is leakage current or saturation current that I discussed earlier. So basically, eta you can calculate. Q is, you know, the constant charge of electron, Boltzmann constant, and temperature that we have used 26 degree, like 300 Kelvin. The slope, see here, from here to here, this part tells about the rate of recombination. So you have to take slope from here to here and just simply put here, and you can calculate the value of eta. Ideality factor that you can calculate from here also, or you can directly see from here, the leakage current or saturation current. If this part is more linear, that means ideality factor is high, like you see in this case. But if this part is non-linear, that means ideality factor is less or less. What is mean? Like 1, 2, or 3. This is the just numeric number. These are the when we keep fixed and when we keep moving holder in sputtering, then we have seen how efficiency varies, and best result that I have gotten for 2 nanometer thin film is around 2.27. It means we have taken silicon. This is given here. The efficiency was 13.63, and we deposited a NiOx thin film, and efficiency, solar efficiency suddenly enhanced 15.90, and that is quite different way to explain, like size, when we use NIUX, that is quite different from NIO, that means creation of vacancy. So a lot of such factors play an important role. Obvious surface roughness also one of among them. Towards the thin film solar cell or solar cell, one important part is down energy conversion. Maybe you have heard about up energy conversion or down energy conversion. So I will discuss here about down energy conversion. That is quite interesting to understand. What does it mean? It means we have our panel or solar cell. If sunlight which is coming from any random source, if light is coming, then I earlier said only light can be absorbed by material if they have band gap similar to upcoming light source. For time being, you consider we have chosen certain material, they have larger band gap, or in that case, light cannot be absorbed. Okay, light excess of energy, which is coming from sun or any random source, which has energy higher than band gap. If they have energy equivalent or lower than band gap, it's okay. But they have energy higher than band gap, then is it absorbed by material? So answer is no. This energy is emitted or back as a reflector directly. So high energy photon with energy, like here is given, is equivalent to 2 EG. Like if we are talking about silicon, band gap is 1.2 electron volt, like is the sunlight which is coming having energy around 2.4 electron volt, light equivalent to 2 photon. So obvious, if coming light and band gap that is not matchable, then that light might be reflect or get back. So in that case, we have to take one layer over the material to convert this high energetic photon into different photon. Understand? Material required 1.2 electron volt energy only, because that is optimum band gap of silicon cell. But sunlight, which is coming having high energy like 2.4 or 2.5 electron energy, so that energy will never be absorbed by material because it is larger than optical band gap or electron affinity, that I will discuss later. Okay, so we will decide, we will deposit, we will coat, or we will evaporate a layer over the silicon substrate that has ability to convert these two EG equivalent photon in two different EG. Energy advantage is now this EG photon, like this photon having band gap 1.2 electron volt, and this is also having energy 1.2 electron volt. Now this photon could be absorbed by our silicon material or any such material, because this is this was not equivalent to our band gap, but this was equivalent to our band gap. So this could be absorbed by our material. Now questions comes, what is the condition to use down energy conservation? So first keep in mind the refractive index. Refractive index of N-type material and P-type material should be approximately same. If we are talking about this material, that could be any CDS, SNS, zinc oxide, nickel oxide, that have refractive index. In case of like silicon, refractive index is 1.7. And in case of nickel oxide, refractive index is around 2, 1.9 to 2. So that is close matchable. So you can use down or assume down energy conservation. Also, second principle to use down energy conservation is optical absorption or absorption of light should be lies in range of ultraviolet range. However, that light should be emit in visible range. See, in this way. This is the first and most important characteristic for down energy conservation is always absorption should be lies in ultraviolet range. However, emission might be take place in visible range. So first, we have to take refractive index carefully. Second, we have to see optical absorption age that is here is around 320, 350 nanometer, and emission that comes around 530. So this is in ultraviolet range and this is in visible range. That fulfills the condition of down energy conversion, means high energy energetic photon that comes, and through that luminescent material might be converted into different carriers or photons. So this is another possibilities to enhance the short circuit current and obviously potential and solar efficiency. So our result that we have explained through down energy conservation also. Now come to the next part that I will discuss also. More interesting, earlier I was discuss about nickel oxide, zinc oxide, but can you assume if we deposit metallic layer in the sense silver, gold, copper, chromium, nickel, cobalt, that is quite different from semiconductor, because semiconductor that has band gap. So we could explain on the behalf of band gap if energy have band gap equivalent to this one. But in metallic, we know conduction band and valence band, they overlap each other. So there is a no balance energy band gap. So how we will explain, we will see later. So this is optical data of silver nanoparticles that we have deposited over substrate. That is here we have taken glass substrate, and this is SPR, like surface plasmon resonance. In case of silicon, silver is around 420 to 450 nanometer. Surface plasmon resonance is nothing. It's just if we take two layer, one is silicon, one is silver, then vibration or oscillation of electron at interface of these two layers. If this is silicon and this is silver, then electron and hole, which is vibrate or oscillate in this interface, that is called SPR, surface plasmon resonance. So these are the solar efficiency. See how color varies. If we code 0.5 nanometer silver, then see color is blue, because this is ultra thin layer, and silver has stable capability to trap the light. But if we are taking about reference 20 nanometer, see color is getting black because thicker film don't have tendency to enhance the efficiency. And see here, blue indicate a reference and 0.5 is above red, means short circuit current is increasing. That means solar efficiency could be enhanced. But in case of 20 nanometer, we are talking, see here, reference is here, and when we coated or deposited thicker layer like 20 nanometer, 40 nanometer, then see short circuit current is reduces or minimized. It means it is confirmed from here, thicker film don't have capability to trap or penetrate the carrier inside. So please, when we select the material, we have to carefully optimize the thickness of each layer. These are the parameters. We have calculated short circuit current, open circuit voltage, series resistance, parallel resistance, fill factor, solar efficiency. So instead of metal oxide, you can also work with metallic layer. Now come to the more and advanced result. Texturization of silicon solar cell. I earlier discussed about the Martin Green. We used pyramidal silicon or pyramidal structure instead of plain silicon to enhance the solar performance to trap the light. So these are the process through which we can texturize the silicon. If we take silicon, we have to clean it, and we can deposit silver nanoparticles. I will discuss later what is the role of it, but you can deposit through physical technique like thermal evaporation, sputtering, electron beam, or through chemical. It's quite simple to deposit through any precursor like silver nitride, silver chloride, and later you have to etch with HF plus H2O2. So here the condition, we have taken different wafer with same resistivity, and this is the etching time. Etching time means I will show you later how I did. How time we have and deep in this solution HF plus H2O2 like 5 seconds, 1.5 seconds, 10 seconds, this, and maximum is 1 second. and concentration of HF and H2O2 that I kept fixed 4.6 per HF and H2O2 is 0.5. And advantage is, see, the reflection in case of silicon is around 66%. If you search on Google, the reflection of silicon or polysilicon is around 66% in visible range. Okay, but when we texturize same silicon through this method, see how reflection are reducing. See here, in case of this is around 70 to 80%, and when we put few layer, it reduces below 10%, like 6%, 7.5%. See here. So this is another idea to enhance the light trapping behavior in our device, and that you can implement for photodetector, for sensor, any such device where we have used to enhance that light trapping or absorbing capacity. So if you use texture silicon or porous silicon instead of pure silicon, then you could get better outcome. Here, we have uses solar cell substrate. After texturization, we have deposited nickel oxide thin film in terms of NiOX. And in second part, we have deposited NiOX and silver, and we have studied different outcome. If we compare texture silicon, this is here, and we have deposited 1 nanometer, then short circuit current is rapidly increased. But in case of 20 nanometer, we have gotten some negative outcome because of thicker layer. See here, here the real picture that we have taken from our laboratory. This is without texturization silicon, and this is texture silicon, also called as black silicon. I will discuss later what is the concept of black silicon. So porous silicon or texture silicon is also called as black silicon. You can see after and before evaporation or deposition. If we take normal substrate, then current is increasing rarely. But if we use texture silicon, then current is rapidly increased. I will discuss mechanism later. That is called multiple scattering that take place in that direction. So design of advanced solar cell is also come in that direction. We have to take silicon. We have to deposit with silver layer through either physical technique or chemical technique. Once silver layer is deposited here, we have to dip that in presence of HF and H2O2 solution. Okay. After the mechanism, the creation take place. This silver layer will reach here, and later we eliminate this silver layer using HNO3. Using HNO3, we can eliminate silver layer from here, and later we can treat with HF to eliminate oxide layer which is present in our substrate. Here, this is the more effective diagram. Silver, we can dip inside the beaker where we have solution of precursor AgNO3, this one, and we can deposit this one, and later this we can put here in mixing solution in presence of H2O2 plus HF, then we can get in this way, and later we can remove the silver here, and further in next step we can use HF, hydrogen fluoride, to eliminate oxide or nitride layer which is present here. So I was before 1 week or 2 weeks ago, I was discussing with someone. He said how you can claim silver is removing from here. If you use HNO3 in this layer, then how you claim the elimination of silver? So answer is we have recorded X-ray spectra. So see here, silver peak that is absorbed recorded around 380 nanometer, but no silver signal is observed here. So first confirmation is there is no silver present in our sample. Okay. Second, how we can claim to remove oxide, because if we take silicon, then one SiO2 layer is always present over silicon. How we can claim to eliminate oxide layer with using HF in final sample. So here, see, if we use silicon 2P peak in CASA XPS or any such software, XPS software. So you see, this is the 2P 1 by 2 or 2P 3 by 2 peak. And if you see silicon, polysilicon, normal silicon, then you will get one peak is around 103.2. That peaks is for SiO2, silicon dioxide. So in our case, there is no peak present here. That means we have fabricated pure silicon base structure. That could be porous silicon, that could be texture silicon, that could be silicon nanowire. These are the evidence towards that direction. Okay. So these are the simple that I was discussing about. We deposited earlier 0.5, 1, 2, 5, 10 seconds for texturization. But when we are making plan to fabricate porous silicon or silicon nanowire, we have to use high etching time like 30, 40, and 50 minutes we have take to texturize the silicon. That comes in category of either porous silicon or silicon nanowire. See here, the result is quite interesting. This for 30-minute etching time and 15-minute etching time. Here I didn't add 40-minute. We have also 20-minute also, but silicon nanowire that has formed for 30, 35, 40, 45, and 50 nanometer. After 50 nanometer, is the saturation point. Nanowire is broken, is divided in different parts. So this is straight and well aligned vertical. So if you use this nanowire for silicon solar cell instead of plain silicon or texture silicon, you will get more effective outcome. See the reflection. In case of silicon nanowire that I reported also in optical material earlier, is around 6 to 7% as compared to polysilicon. That is quite effective and useful for such devices. If we are fabricating advanced devices, then light absorbing, I didn't add here the data that I calculated from FDTD, one theoretical software. The light trapping behavior is quite effective. Mechanism is here. See, we have also recorded atomic force microscopy. If we take normal silicon substrate, what is happening when sunlight which is coming and getting reflect back? But if we use texture silicon or porous silicon or silicon nanowire, so in that case, structures looks like something this. When sunlight is coming here, then this might interact here, this might interact here, this might interact here. So there is a multiple scattering take place here. See, come here and go here, then come here. In that direction, light which is coming here, after interacting here, they will go here, later they will go here. In all these mechanisms, light will absorb and trap by the material. Light, there is a less possibility to reflect the light. Same we have observed here. See, when sunlight is coming here, then due to multiple scattering that take place, one strike here, second here, third here, and finally, after a lot of such interaction, light would be captured by that material. But in case of flat or smooth or polished or normal silicon, sunlight is coming, it could be absorbed. I'm not talking about it totally reflect, because only silicon reflects 66% light. This light might be either absorbed or transmit. But when you complete discuss with the mechanism, then you will get, in case of texture silicon or rough silicon or nanowire or porous silicon, due to multiple scattering, light could be absorbed. Okay. This is the okay. So here I didn't include when we take silicon, then this is p-type silicon, and we fabricated emitter layer here using phosphoryl chloride PuCl3 and thermally evaporated silicon oxide SiO2. That later we are working towards to replace that passivation layer with another material that could be silicon nitride, SiNX, Si3N4, or Al2O3, or mix up of that material, because passivation layer is more important to enhance this current or potential in our device, because see here, if we are taking here, this is our material. This is, for example, emitter here and here contact. Then minimization of recombination in this direction that we can get after the different passivation. So that we are going and working in that direction. And this data has recorded and efficiency that we have got it for 14.26%. That is quite interesting. And we are still utilizing different mechanism to enhance the solar efficiency. If we are using either P-type material or N-type material, and also we will use different passivation layer, different metallic or metal oxide layer, and further having planned to use silicon with perovskite layer. And very recently we are going to start silicon with perovskite layer, like heterojunction with silicon to perovskite towards the tandem solar cell. And reported work indicate that could be more promising for these days. So continue with the different passivation silicon nanowire or different mechanism that I will discuss here. And if I will get some output, then I will further come and will discuss. Thank you.
Sí, gracias, Chandra.
Arturo,
¿Sí? ¿Me escucha? Muchas gracias, Chandra, por la presentación. Este, nos vamos con la sesión de preguntas. Primero los panelistas que siempre están por ahí. Está José Fermín, que tiene preguntas.
El video ahí. Bueno,
Te escuchamos,
hizo el
sí.
video. No, gracias, Kumar. Espero que estés bien. Gracias thank you to all our friends from India to be here with us today. No, Arturo, no voy a hacer preguntas a Kumar. Prefiero pasar mi oportunidad para los invitados, que veo que hay bastantes, ¿no? Sobre todo
Bastante, sí.
algunos de Venezuela, entre ellos el profesor Juan Chirinos de Chile, por cierto, venezolano en Chile. Te cedo el tiempo a ti, Arturo, para que se continúe.
Claro, gracias. Entonces, con Chirinos, está por ahí.
Juan, Juan, ¿estás?
Juan Chirino.
Sí, Juan Chirinos es un venezolano que está trabajando en la Universidad Autónoma de Chile, en ciencias de
Bueno,
material.
parece que
Sí,
sí
bueno.
está, pero no responde. Entonces nos vamos con otro.
ऊपर से आ गया वो
तो भाग जाओ मैं तो 4 काट दूंगा 1 घंटा लग जाएगा
Bueno, no sé quién está hablando.
मैं तो डर सा लग रहा है
ये क्या है
Nos vamos con otro.
रोटी खाने का बच्चों को छोटों को
Vámonos con otro participante. ¿Está? ¿Quién tiene activado su micrófono? ¿Que se escucha? ¿Felipe? ¿O está?
हिले लो रोम खत्तर
ये बोल देंगे गाड़ी में रखा ले
Está por... ¿Quién tiene su micrófono? ¿Lo pueden cerrar? Por favor. Se escucha en voz. Está Felipe. ¿Quién lo veo por ahí? Pirela. Pues más bien yo creo que como hay muchos, si tienen preguntas, abrimos el micrófono para la gente que tenga preguntas. A ver,
ustedes pueden escribir en un grupo también, acá.
sí, podemos escribir en el chat. A ver,
Sí, claro, pues en chat. Pero no lo vi nunca el pregunta, porque
Maggie
mira,
dice que no tiene.
I
Buenas
have a
charlas.
question, if I may.
ya, sí,
Mario Reyes, adelante.
Yes. Hello. Thanks for your talk. It's a curiosity. My field is not solar cells. My field is magnetism. It's only a curiosity. You have presented a picture of the efficiency of the
ya,
solar of the materials as a function of the years of the published materials.
ya.
And I don't know that picture. I found that picture here in my computer, and it is very interesting that picture because summarize all of the materials for the last I don't know 50 years, and I was looking at that picture, and I saw that oxides and efficiency ranges from 15 to 50 percent. And my question is only a curiosity. I mean, and oxides are around close to that values that you presented, 15%. My question is, why did you choose oxides, considering there are a lot of materials with enhanced percentage of efficiency?
Okay, so thank you, and it's a nice question and effective question. Actually, I didn't discuss here. The difficulties in solar cell is first difficulties to minimize the cost. Like en español, como tenemos que tomar el material el silicio como el muy barato, no es caro. El primero cosa. El segundo, tiene más que ver el uno cultura, por ejemplo, ahí tiene mejor. Por ejemplo, usando 26% de la eficiencia, la 27% de la eficiencia, pero tiene el cultura, el pre-cultura, la cultura. Pero es muy difícil en laboratorio. La eficiencia como el 15%, 16%, ahí tiene el multicultura. Pero el Antofagasta estábamos usando como el silicio con la ultra fina película delgada. El beneficio por el muy barato. Además, donde podemos tomar el foto, el datos, voy a escribir en su correo. Por favor, puede escribir en su correo el página del Martin Green, el profesor de Australia, ¿ya? Ahí tiene todo cosa para la evidencia, el generación 1, el generación 2, el generación 3, el película, la orgánica, el perovskita, la toda eficiencia como esto.
I see. So the main reason is the price of the material,
Actually,
because oxides
there is a one reason to we have to choose material because solar cell they are suffering in three directions. One, to minimize the cost. Second, to enhance the efficiency. And third, to enhance or maintain the lifetime. So
Okay.
that doesn't matter if we design any device, four layer device that has gotten 48% efficiency, but that is more expensive.
Okay, I see. Okay, understand. Thank you for your attention.
Yes.
Gracias. No sé si tengan preguntas por ahí. ¿Más? Jimena, por ahí preguntas de Colombia.
¿Cómo está, profesor Arturo? Profesor también. No, pues por mi parte no
¿no?
tengo preguntas y estábamos revisando acá en las redes y no hay preguntas para el que hizo la exposición el día de hoy. Eh, Muchas gracias, profesor, y muchas gracias por la charla. Muy interesante, digamos, lo que se está haciendo al respecto.
Gracias.
Gracias. ¿Quién más por ahí?
Por ahí está María Pirela de Lille, Venezuela.
Pirela.
Y está la profesora Blanca también de la Universidad de Oriente. No sé si tiene preguntas ahí.
Blanca, ¿tendrás preguntas? Eh,
Días.
buenos días.
Muchas gracias por el trabajo, se ve bastante interesante. Me pareció la aplicación de las nanopartículas, la capa delgada de las nanopartículas muy interesante. Este, pero no tengo preguntas al respecto. Muy interesante el trabajo.
Muchas gracias, María. Yo creo que ya no tienen más preguntas, ¿verdad? Hay de tus invitados, Chandra, ¿tendrán
Profe,
preguntas?
sí.
Are there any questions
¿Me escucha, profe?
from India?
Okay.
Questions from
So,
India?
okay. So, let me see. Anurag, are you here? Probably there. El profe Antonio, ¿me escucha?
Antonio, creo que ya tiene micrófono, sí. No,
Agar,
parece que tiene problemas de audio, sí. No podía hablar desde la mañana, ¿no?
el Zarate
Este,
tiene el problema en su audífono, el
sí,
micrófono.
claro. Sí, sí. Pues yo creo que no, hay más preguntas. Chandra, muchas gracias
Ya, no
por su
importa, profe,
exposición.
algo quiere, podemos discutir en coreo, por ahí.
Sí, si tienen preguntas o comentarios, podrían mandarle un
Sí,
correo a
sí,
Chandra
sí,
directamente
también,
por ahí por su correo.
porque mira, ahora trabajo acá el mismo como el magnetismo, él también.
Ajá, está bien.
El para supercaptadores también trabajo en el mismo grupo acá. El
Arturo, hay
vento.
una pregunta por el chat.
Ya, a ver.
Ah, sí. Sí,
How
hay
did you
una pregunta,
perform
sí, ya
a
la acabo de
Monte
ver.
Okay.
Te preguntan, Chandra,
Profe, actually,
que realizaste algunas simulaciones en Monte Carlo.
usted sabe, no lo uso el Monte Carlo, uso para la property de aplicar el teoría de mí, como my theory, el además uso el DFT, el DTD, el Density Functional Theory. I didn't use Monte Carlo for the simulation purpose. So we are working in experimental field and optical data we use through my theory, FDTD, finite domain disk, and DFT, density function theory. So we use the simulation or theoretical tool towards the optical analysis. And Monte Carlo, in future, if we will use, then we will discuss. And our group is focused only on the experimental research.
Ok. Bueno, Chandra, muchas gracias por tu charla. Entonces, si tienes algo con qué cerrar,
Gracias, profe, por su invitación. Escribo no.
¿no? Gracias por la aceptación. Entonces, y pues damos por terminada la charla y si le decimos adiós lo despedimos a Chandra. Si pueden abrir sus cámaras, por favor. No, despedida.
Luego,
Hasta luego.
Gracias,
Nos
gracias.
vemos. Adiós.
Chao, profe.
Gracias.
Chao. Muchas gracias.
Chao.
Chao.
Gracias.
Feliz día. Gracias.
todos, que estén bien.
Ximena, cerrar transmisión.